And
That's
it's talking about the challenge of modelling waves in the Southern Ocean. So, Marzieh, can you take it away?
Yeah, can you hear me?
Yep, we can't see your screen though.
Oh, you cannot. Okay, just a second. And share again. Oh wow, I'm not sure what's happening here, but can you see my screen now?
Yeah, it's working now. Yep, it's all good. Okay, nice. Take it away.
Great. Thanks so much for the introduction. I'm going to talk about the challenge of modeling waves in the Southern Ocean. This is a work done during my PhD studies at Melbourne University in collaboration with Dr. Lotfi Aouf from Metro France, and all done under supervision of Professor Alessandro Toffoli. Well, first of all, let's see. Let's make sure we all know where Southern Ocean is. Southern Ocean is the body of water below the land masses of Australia, Africa, and South America. It is also referred to as the band of water below the 60th parallel. And why are we interested in studying Southern Ocean? Well, this region is dominated by strong westerly winds that fuel the Antarctic circumpolar current. On top, they give rise to some of the fiercest waves on the planet. The combined effect of these fierce waves and Antarctic circumpolar current make a deep mixed layer in the region that gives the Southern Ocean the capacity to store heat and gases more than any other latitude band on the Earth, making it a major driver of the Earth climate system. Here on the left, you can see some of the main processes in the Southern Ocean, including the track of westerly wind and the CO2 uptake. Despite its importance, the Southern Ocean has been highly undersampled. Not much observations have been conducted there, as you can imagine why. It is a remote region and is of a very harsh environment. The fact of it being undersampled has led to biased wave predictions in this region. Here on right, you can see the normalized bias of significant wave height from a wave-wash-tree wave model. And as you can see, in the Southern Ocean, the extreme biases are evident. Aiming to fill this gap within an international initiative, Antarctic Circumnavigation Expedition took place, which was organized by Swiss Polar Institute. If you have joined previous KOZWaves, you have heard me talking about it a lot. For those of you who have not been in previous KOZWaves, I would just tell you that this is an expedition consisting of 3 main legs that took place in austral summer 2016-2017 from December to March, and went all around Antarctica, during which in addition to many other projects, there was a project in which used the wave and surface current monitoring system, which I would call WAMOS, to collect basically sea state observations from during the whole expedition. The system was connected to an X-band marine radar, as you can see, was deployed on top of the ship here. I won't go through its detail more than that, just mentioning that it gave us in situ observations of wind, wave, and surface current. We have published this data set and a manuscript about it, and I would refer you to check it out for further details. What I'm going to concentrate on is a wave model that we set up based on these observations to basically assess the biases in the Southern Ocean to figure out what is happening there. What we used was the wave-wash-tree wave model, which is a spectral third-generation wave model based on a numerical solution for wave action balance equation, in which wave evolution is controlled by the sum of source terms that describe the physical processes. Main physical processes in deep water in Southern Ocean where we are the nonlinear wave-wave interaction that we have modeled with the NL1 source term, which is based on discrete interactive approximation, and the two other physical phenomena happening there, main physical phenomena happening there are atmosphere and wave interaction and wave-ocean interaction that we have modeled that with SD6 source term. The model is set up in 24 arc-minute spatial resolution and 20-minute temporal resolution. We have calibrated and validated the model covering the period that Antarctic circumnavigation expedition, which I'm going to call ACE from now on, has taken place. And we have used the wind and ice data from ECMWF aerophile reanalysis and current data from GLORIS. Just a quick background on how the calibration takes place using the SD6 source term in WaveWash 3. Well, SD6 does a bulk adjustment of the wind field by rescaling the drag parameterization. This drag parameter CD factor that I'm going to call CD fact from now on depends on the wind speed. The model is very sensitive to this factor, as you can imagine, because it's basically related to drag parameterization. And what I did was to calibrate my model for the southern hemisphere. The default value of CDFAC is 1, and by increasing it to 1.05, I could get a calibrated model for the southern hemisphere. Then I validated my model. Well, both calibration and validation was done against satellite altimeter observations of significant wave height. And here you can see the result during my validation period. In general, model is doing pretty good job. However, there exists some biases spread around Southern Ocean and some more extreme biases with as you can see, that are closer to the Antarctic continent. The red values basically show the model overestimating the wave height in the region. Referring to the literature, it is suggested that these biases can be reduced by inclusion of current in the model. So we gave it a try, and bizarrely enough, we realized that, well, actually, there is a slight reduction in the biases in the Southern Ocean, but not much, and the bias closer to the Antarctic continent actually doesn't change at all. And the change in our root mean square error for significant wave height, when comparing it against when we force the model with wind only, and then when we force the model with wind and current both, is less than ½ centimeter. Being puzzled by this result, we try to look at the model to see, okay, what basically happens when we include current in our model. WaveWash 3 wave model sees the basically accounts for the effects of current on wave number shift. Also, it corrects the wind speed for the current speed. In this equation here, the effective wind speed on the left is the wind speed minus a proportion of the current speed. This proportion is set to 1, basically 100% of the current speed as default. However, it is suggested to be put as 0.5, half of it. The point here that has been missing in the literature is that when we add current in the model using this switch that has been integrated in the model, we are basically changing our wind field. By change of wind field, we would again need to readjust our CD factor. So again, a very slight change in the CD factor. As I mentioned before, the model is very sensitive to this parameter. But still, when we go through this process correctly, it turns out that, well, actually inclusion of the current cannot help much in reducing our biases in the Southern Ocean. Another thing to look at was to make sure we know what we are feeding into the model, how good as our current is. And from our observations during ACE, we had the surface current, so we could compare the current that we are feeding into the model against our own in situ observations. It is interesting to see that actually the current speed is underestimated by GLORIS by about half. So we thought, why not to compensate for that by doubling our current and see maybe if the current was actually right, we could see a change in our bias. Wow, yeah, but we couldn't. We doubled the current this time, fed it into the model, and again we saw, okay, maybe a slight reduction in the bias, but the main bias is still there. So we thought, okay, let's look at the basic physics of it and guess how much basically we should expect from the current to affect our wave field. Here, I have plotted the dimensionless current speed, which is basically the current speed over the group velocity of the waves. And as you can see, most of the times, the current speed remains, basically this ratio remains almost all the time below 0.1, meaning that the current speed is less than 10% of wave group velocity. And rarely does it exceed 0.05, meaning 5% in these regions. I will come back to this plot, but just before that, I would explain what I'm showing here on top right. It is showing the difference between direction of current and wave, with values under 90 degrees showing that currents and waves are following each other, and values above that showing that they are opposing each other. As you can see, where the Antarctic circumpolar current exist, they are mostly following each other, and below South Africa, they are opposing each other. And down here, I'm showing the difference in our significant wave height from the model with the actual values of current on the left and with doubled values of current on the right. It is very interesting to see how these plots changes in the significant wave height and the dimensionless current speed match. Basically, wherever the slight changes in our significant wave height match the areas where this dimensionless current speed exceeds 0.025, which means 20%. So if we were going to get difference in our biases as a result of current, we had to give it along this narrow bound here and not for the whole biases that were spread all around Southern Ocean. One other question to answer here was that very high biases in regions closer to the Antarctic continent. To explore that further, I have plotted basically the Era 5 wind that I'm feeding into the model against satellite observations on top here for 3 different months, and down I have plotted the wave height that I'm getting out of the model against satellite observations again. And on top I have plotted the outer edge of ice, the maximum ice during that month. So it was interesting here to see that the high biases of wind basically are bound within this edge of ice around Antarctica during all 3 months. And as you can imagine, these biases are passed to the wave model and to the significant wave height that we are getting out of it. And more or less for the wave heights, this ice also, the biases are confined within the limits of the ice during that month. Now that we have the model set up, well, from before we had these in situ observations during ACE from WAMOS, now we have our model set up, we know what to expect from it, and now we can compare our model against in situ observations that we had. As you can see, the model again is doing a pretty good job in general, however, the wave height is still a bit overestimated. The mean wave period is pretty good, surprisingly, except at the second leg of our expedition, which has happened here at regions closer to the Antarctic continent. if you refer to that paper, our manuscript from WAMOS observations, you will see that the WAMOS gives us the full directional wave spectrum. So we were able to actually compare the wave spectrum from WAMOS against our model. I have also plotted the concurrent observations from SAR satellite observations to see how they compare. It is interesting to see that the wave model pretty much in this case combines the two modes of this wave spectrum. One other thing that we were interested to look at was to see how other global wave models basically perform against our in situ observations. Here I have plotted the significant wave height, wave period, and directional spreading from CAWCR hindcast, which is a hindcast that's used for marine forecast at Australian Bureau of Meteorology. As you can see, however, this directional spreading is pretty good. The significant wave height and the mean wave period are overestimated significantly. How about error 5 reanalysis that basically includes assimilation in the model? As you can see, this time we are getting a much better results for the wave height. However, the wave period is basically underestimated here. To put it all in a nutshell, I wanted to basically give you a very quick introduction how important Southern Ocean is in terms of its the role it plays in the Earth's climate system and how little our knowledge is of waves in this region. Again, the Antarctic circumnavigation expedition that has provided us in situ observations in the region is very valuable for studying waves here. And that's what we did with setting up a wave-watch wave model based on our observations and looking at the results. One of the outcomes of it was to know that we should not expect much from current to contribute in reducing our prediction biases in the region. We have also compared our data against, well, basically, I should say, the models against our in situ observations, and we saw a significant overestimation of CAWCR hindcast, but the error 5 reanalysis, which benefits from data assimilation, gave us a much better approximation for wave heights, which may be indicating that the assimilation is the way to go for reducing wave prediction biases in the Southern Ocean. Thank you for your attention.
Thank you very much. Is there any questions for Marzieh? I can ask a quick question while we wait, but I just wonder, you know, are these errors